Hello, so in this video we're going to look at how we could use a graphical method to measure the acceleration due to gravity, or this is normally referred to as G by freefall. So what we're going to start with is thinking about a little ball falling from rest, and it's falling a certain height, and that height we're going to call S. And we're going to time how long it takes to fall that far, and from that information, knowing that it starts at rest, so the initial velocity is equal to 0, we could use one of our Suvat equations, S equals ut plus half at squared, knowing that the initial velocity is 0, we lose that term and we get that the displacement, or the height that it falls through, focus that, the height that it falls through equals half a t squared. And this a here is our acceleration due to gravity, or little g. So we can measure all these things and we could get a value. But just doing it once like that is a little flawed. We won't take into account any random errors that might be there. We won't actually know that the acceleration due to gravity, which we think is constant, we don't know that it's constant by doing that measurement. We might, the world might work in a way that we don't expect, and the acceleration is less at first and then increases. We want to confirm that this relationship is true, and we want to get a good value for G. So the way we do that is by taking multiple measurements and processing the data in a particular way. So I'm just going to move that out of the way and look at how we'll do that. So the idea is this. We're going to start off with the same expression, S equals half a t squared, but we're going to basically consider lots of different heights. We're going to drop a ball from multiple multiple heights, so we get lots of different values of S and measure the time it takes to fall for each of those heights. And we're going to try and process that in such a way that it will show us that the acceleration is constant, and will also give us a value for the acceleration. And what you have to do is you have to think about the equation of a straight line. Y equals mx plus c squared. But no, it doesn't plus c squared, it's plus c, isn't it? But there is no plus here, so it's just y equals mx. So this tells us that if we were to get multiple values of s, we could plot those on the y-axis, and if we plotted t squared on the x-axis, the gradient of our graph would be half a. So it would be half of 9.81, hopefully. So that's what we do. I'll just shift that down slightly so it's at the top of the page. So we plot a graph, S against t squared, we get a straight line, gradient equal to half a. Now you might notice that this is slightly unconventional because we're changing the height, so that's our independent variable, and our dependent variable is the time it takes to fall, and then we've squared that. You would normally plot this graph the other way round. For convenience, and so that you can instantly spot when you look at the gradient whether you've made a mistake, we've chosen to plot it this way. You could plot it the other way, but the gradient would be 1 over half a, and I just find that a bit more painful. So that's what we're trying to achieve. The way we achieve it, move my bit of paper over here, is that we're going to start with something that can drop a ball. And this thing that drops a ball is going to be connected to a timer, and it's going to fall a known height, and that height's going to be measured with a meter ruler. So this is our S, and then it's going to hit a pressure switch. Now there are many ways of doing this. Sorry, I'm not getting it off the page. There are many ways of doing this, but this is the equipment we've used. And when the pressure switch is hit, sends a message to the timer to stop timing. And that's our G by Freefall experiment. Now a couple of things to bear in mind is when you're recording your information, you need to record it in a table as you go along. So I'm going to shift this over and show you the sort of table that you might end up with. So we're going to do a range of different heights, and I'm going to indicate that I've measured that in meters. I'm going to do a range of different times, and I'm going to measure that in seconds. And then I'm going to process that, and I'm going to have t squared, but I've got to remember that if I've squared time, the units are going to be in seconds squared. And then I might go 1, 2, 3, and a mean. And then I can box my table out. And I've done this for a reason, because I just wanted to show you a couple of bits about this where you could go wrong. One of the problems is what you write in here. Because if you put the height at, say, 10 centimetres, you might be tempted to just write, 10 centimetres is 0.1 metre, isn't it? But you've used a metre ruler. And the metre ruler measures to the nearest millimetre. So you should write down what it actually measures, or what it actually says on your measuring device. So 10 centimetres, but it also measures millimetres. So you should write 0.100. And what you'll find in these columns, and they're actually assessing this quite a lot at the moment, which seems a bit odd, but it's a thing that the examiner seems to like, you should have the same number of decimal places. Now there's some confusion here. Sometimes people think it should be the same number of significant figures, but that doesn't make sense, because if we went on to reach a full metre, it would still be reading to the nearest millimetre. So when you look down this column, you should see the same number of decimal places. Same in the timing column, because you've measured it. So the same here as well. But when you come to actually process your data, so anything where you've multiplied something by something else, etc., this one, same number of decimal places, is no longer the rule. The rule is the same significant figures. And when you look down this column, you should all have the same number of significant figures. And you might question how many. So what you would do is you would look to your other columns and see generally what you've got. And I think conventionally you would go for the smallest number of significant figures, but really what the examiner's looking for is something sensible. So if you've got 3 significant figures in this column, put 3 significant figures in this one. That's pretty important. And that's it for the G by Freefall. I'll do another video on looking at the uncertainties.